but here's the review. I think this is what we covered, right? After the first exam. And we just kind of hit the highlight topics. And so the way that I would suggest you study for it is you just go through these topics and then you highlight the topic when you believe you have pretty good knowledge of what's going on, right? You can also add notes like this is in page, or this is in this is on video, blah, blah, blah. And, certain times, if you want to break it down that way, that might be helpful as well. I also encourage everybody to rewatch the videos because you can watch them at 1.5 times speed. That's what I find comfortable. So an hour video, you can get by in 40 minutes, right? So you don't have to sit there and do it all. But when you get to a point where you're not sure of something, then you can slow it down. So it's a much more efficient way to do things. So take advantage of the technology. It's great. I was actually watching, my son did a couple basketball games this weekend, and I was putting together the game video for his coach. And instead of, having all this sitting around timeout stuff, I just would edit the files. And it's so easy to do. So just take advantage of it. I don't edit these video files because what I think is not relevant may or may not be important. The only thing I would cut out would be the 5 minutes of sitting time. But some people actually like the 5 minutes because they think, hey, I don't have to time myself. But if you're watching it in TV land, you can just kind of skip ahead pretty easy if you want. So I kind of waffle on that. But here are the major topics. And again, we start right out with item number 1, use the Shomes outline series for practice problems. There's 2 Shomes outline series I would suggest for this one. The first one is what we've been using, right, at the beginning of the semester for the electric circuits. The other one is for doing control systems, because that's where you're going to get a lot of practice with Laplace, okay? So if you need additional practice problems, you can always print out those. They're like $15-20 to purchase from Amazon, and you can access PDF, so you can get them immediately. But we kind of started out with combining capacitors and inductors. So we were looking for equivalency. And what we saw is that capacitors in parallel add like resistors in series, and capacitors in series add like resistors in parallel. So that's opposite, right? For capacitors, it's the exact opposite of resistors, where inductors is exactly the same. Inductors in series add like resistors in series. Inductors in parallel add like resistors in parallel, okay? So when you're trying to do this work, because if you have a circuit that you're trying to get a time constant or whatever, it's important to simplify that down to one individual inductor or one individual capacitor. Okay. So then we moved on to our generic equation. If you don't remember, this was our y of t equation. And if you remember, it was y of t is going to be equal to y of infinity plus y of 0 plus minus y of infinity e to the minus t over tau. That's if you have any first order circuit, if you can solve for those y values, either voltages and currents, you can solve for any particular y of t equation, voltage or current, for any circuit element. Doesn't matter. You just need to be able to solve for that. The hard part is the t equals 0 plus or 0 minus. So remember, when you are going to solve for t equals 0 minus is when you can't have an instantaneous change in the quantity. So for capacitor, your voltage can't instantaneously change. So at that point, you definitely want to solve for the t equals 0 minus part. And then you don't have to solve any more, because the 0 minus part is the same as the 0 plus part. They're the exact same quantity. For an inductor, it's the opposite. It's current. So you can't have an instantaneous current change in an inductor. So the t equals 0 minus parameter will be exactly the same as the t equals 0 plus parameter for the current in an inductor. When you do need to calculate the t equals 0 plus, right? that's when you actually are trying to solve for the current equation in a capacitor or the voltage equation in the inductor. So if we want to append over here, we would solve for VC over here and IL. Over here, it's IC and VL. So if you're looking for the T for either of these two, IC or VL, you're going to have to set up an additional circuit to go ahead and solve for the parameters, because that voltage and current can change instantaneously. And you'll have to modify the circuit by grabbing either the VC or the IL and redrawing your circuit with that initial condition, because those initial conditions are what's going to determine the IC and the VL. Okay. So remember, you have to do that additional step if you're going to go through and get those. Everybody understand that? We went through quite a bit of those, but I want to just kind of review what we talked about there. So once we get the VC of 0, either minus or plus, or not VC, let's just go V of 0 minus or plus, I of 0 minus or plus. The only thing we need now is the Y of infinity. All right. So at that point, you just open up or short circuit as necessary, because you're assuming that there are no changes in your system. So you can replace power supplies or inductors. You can't replace power supplies. You can replace inductors and capacitors with opens and shorts as necessary, so you can calculate your final conditions. So at most, all right, at most, you will have to draw 3 circuits to calculate these parameters here. Right? And why do I need 3? Because I will need that one to get my initial conditions to solve for the 0 plus. Okay? That's at most. The minimum you need to do is actually have 2. Then you have to do an additional circuit, right? And the additional circuit is solve for R Thevenin, because that's what the inductor or the capacitor are going to discharge through. That's what that inductor capacitor sees externally as limiting the current flow out. So you need to make sure you're figuring out all that value of resistance there, which means solve in any way you want. If you can, it's usually easier to turn off all independent sources and replace them with their equivalent internal impedance. So you do opens and shorts. If you can't do that, if you have a dependent source in there, right, that gets to be a lot harder with a dependent source. Then you got to use either the test system or find V Thevenin and I Norton and do those type of things. Okay. That would be the additional step that you would need to do that. But that's the only other thing we need to worry about. And then our time constant is either RC or L over R, right? Depending if it's a capacitive resistive circuit or an inductive resistive circuit. There's no time constant if you have no resistance, because basically what you're saying is that inductor or that capacitor charge up instantaneously. There's no limiting factor on that. All right. Which it shouldn't be, right? Because the capacitor can't instantaneously change. But an ideal voltage source, I think, rules the roost and says, nope, you have to be at my voltage, right? Realistically, that's not going to happen in the real world, but that's why you always should have some resistance in there to kind of keep things at a reasonable pace, because they will charge or discharge very, very quickly. One of the things that my dad used to do when I was a kid is you would check the charge state of a capacitor. So what would you do? You just put it across a piece of metal and you'd see it arc. Oops, no, I guess it was charged. Maybe we should have done that. And that's how he also tested to make sure the capacitor was good. I don't know if that was the best idea, but it did what it was supposed to do. So that was the big thing that we did for living in the time domain, right? Because this was the first time. Wait a minute. I'm missing one here. Sorry about that. Oh, here it is. I skipped this one right here. Energy storage in capacitors and inductors. Because you can store energy now means you have waveforms, right? So you should be able to draw V of t, I of t, P of t, and W of t. So let me put that over here. P of t and the work. Remember those equations, those graphs where we were coming up with things? And how did we do those graphs? We started with tables, right? T greater than, let's just take 1. And then we saw, is it the integral of the derivative, right? When we were going up and down and things, and we were coming up with those time intervals. And once we set up those time intervals, we were able to draw the plots pretty easily. But remember, if we don't have an instantaneous change, let's say it's I for this interval, remember for the next interval, we just copied that down. That would be the start. So like the voltage in an inductor can change instantaneously, so we don't copy that down. But the voltage in a capacitor does not, so we could go ahead and copy that down. We also copied it down for work, right? Because the work in any circuit can't change instantaneously. You can't go from 5 joules to 0 joules instantaneously. You've got to go from 5 joules to 4.99 to 4.98, et cetera, et cetera. So the work one was also where we had those connections there. Power can jump up and down, no problem, because our voltages and our currents can reverse direction. And since you're just multiplying V times I to get P, your directions can, you can change instantaneously, no problem. Okay, sorry, I skipped through that one. Then we did Laplace, right? So we spent a fair amount of time getting to this point. We want to make sure we're all comfortable with all the circuit analysis and everything makes sense. And then we started introducing time domain stuff, and we started to see some differential equations. But since we don't require you to do differential equations, we are going to focus on doing everything in Laplace. So we've got to get familiar with it. And that's what we did. So we did our Laplace transform. If you don't remember, f of s is equal to the Laplace transform of f of t, which means we take our f of t and integrate it from 0 to infinity, and we convolute it with e to the minus st dt. That's just the generic way to conform or to convert from the time domain to the Laplace domain. And when we did that, we had bunches and bunches of them that we derived. Remember, we did the unit step function, which wasn't too bad. We did a decaying exponential that wasn't too bad. Then we started getting into more challenging ones, including sines and cosines, where we had to do a lot of work to introduce Euler's identity and go ahead and represent the term, a little bit more straightforward. But that was the first time when we started to see that a cosine or a sine is e to the j something minus or plus e to the j something over a number, right? So we actually started to see, oh, wow, these complex exponentials, if we put them together properly, will give us sines or cosine. So that was all the Laplace transforms. Make sure you understand well enough so that you can do an easy derivation. I'm not going to expect you to do a crazy one, but just do a fairly simple one, or possibly like a unit step or an exponential decay. And then that's the transfer to go to the Laplace domain. Once you did the derivations, then you can just make it look like the tables, right? Use it and look like the tables, and then you can go directly into the Laplace domain. So unless I tell you specifically to derive it, don't do it. Use your tables. That's why I say use the tables of Laplace transforms. So there's 2 different tables, right? There's the Laplace transform tables, and then there's the math properties, or the properties of Laplace transforms. So you should be able to use both of them, but the Laplace operations is not as important as having the Laplace table, as long as you remember a couple of key properties of Laplace. What are the key ones? Adding and subtracting in the time domain is exactly the same as adding or subtracting in the Laplace domain, which is a good thing because it allows us to use partial fraction expansion. If we didn't have that, we could not do partial fraction expansion. Multiplication by a constant, right? Not something that is varying with time, but multiplying by a constant in the time domain is exactly the same as multiplying by that same constant in the Laplace domain. All right. which that is huge because the plus minus part, in addition to the multiplying by constants, allows us to do partial fraction expansion. If we didn't have those properties, then we would be, this method wouldn't work. And the last one is the most important one, because multiplication by two functions in the time domain is not the same as multiplying by those converted functions in the Laplace domain. And because of that, we actually have to do partial fraction expansion. Multiplication in the time domain has to do what's called, or multiplication in the Laplace domain means you have to do what's called a convolution integral, which is not super hard, but nobody does it. They just do partial fraction expansion, or they stay in the time domain. What is partial fraction expansion? It's the way of taking those two functions in the Laplace domain that are being multiplied, I should say two or more functions that are in the Laplace domain that they're multiplying by each other, and figuring out how to break them apart so you just have individual functions either added or subtracted. Once those individual functions are added or subtracted, then you can use partial fraction expansion and go back to the tables. Actually, you don't even need partial fraction expansion. You've already done it. So we can just go back to the tables. As long as it looks like the tables, you're in pretty good shape. What are the cases that we talked about? We talked about case one. Doing the partial fraction expansion approach that I recommended in this class is you multiply. So if you have real and non-repeating roots for your factors in your denominator, when you factor everything out, then you just multiply both sides by whatever's under the coefficient you're solving for and evaluate at that root. And you just keep repeating the process over and over and over again until you have all the coefficients. If you have case two, if you have real roots that are repeating, it's a very similar process to find the highest order term. So like the highest order repeating root. So multiply by whatever's under the coefficient of the highest, whatever has the highest root, and then evaluate at the root. But then to do the next one, because you got to expand it all the way out, the next one is you do the same thing. You multiply by the highest order repeating root, and then you take the derivative of both sides. Then you evaluate at the root. And you keep doing that until you have no more coefficients to solve for. All right? So that we try not to do any calculus when we do Laplace, but that's a case, hopefully, where we don't have to do hard calculus. Taking a derivative, hopefully, is not too bad. It's definitely a lot easier than solving a differential equation. And the last case is if you have complex roots. So those will be complex conjugate, right? It's a real number plus or minus a J number. So those are complex conjugates of each other. If you have that, you know your coefficient is going to be complex. So to solve for the complex number, you multiply by whatever is under the complex coefficient that you're trying to solve for. Then you evaluate at the positive complex root. Not the negative, but the positive complex root. Okay? Then you've got all those cases. There's no other cases to worry about. Just remember, when you do your partial fraction expansion, make sure it looks like the table. So for this one in particular, case 3 here, it's very important that you remember, because we're using the sine of omega t e to the minus alpha t. In the Laplace domain is omega over s plus alpha squared plus omega squared. A lot of you will forget that that needs to be omega up there. So make sure when you're setting it up to look like the tables, don't forget you need to have an omega term. Okay? That's a pretty common error that people make. Don't do it. How do you get the roots? If it's a second order or less, quadratic equation. You can certainly plug it into your calculator, but I find it's just as easy to do a quadratic equation. Super duper simple for you to do that. And the very last piece I had, since I'm so magnanimous, I'll give you the two tables we talked about. Why do I want to give you that? Because you have a note card. I don't want you to have to write all these things down. I just want you to be able to use the table. And since you're going to be using the table a lot, Why don't I just give it to you? So that'll be attached or included with your exam. You will not need to bring either of those. Okay. The Laplace operations table will have all the operations, including ones that you don't really think about right now. We talked a little bit about the initial and final value theorems. Remember those? We're not going to worry about those. But the derivative one is pretty helpful. That's S f of S minus f of 0. The integral one, right? 1 over S times f of S. The addition and subtraction one. And it does include the multiplication one, but we're not going to worry about that because, again, we're not going to be doing convolution integrals by any stretch. And then the tables will have all the basics. All you really need to worry about is unit step, because that's a DC. Decaying exponential, because that represents the natural response of any system. And then the sine term, because if we have to do partial fraction expansion, we're always going to make it look the sine term. You do need to consider the cosine term, though, too, because let's just say that it looks like the table exactly. You can just go ahead and manipulate it to go ahead and represent it. So that's your first step when you do partial fraction expansion. Make sure, do I actually need to do partial fraction expansion? Do I actually have two functions that are multiplying each other? If I don't, then I'm just going to make it look like the table. So I'm going to adjust as necessary to get that to look like the table. Everybody understand what I'm saying? That should be your first check. Do I even need to do partial fraction expansion? So don't just jump in and see something that has an S squared there and say immediately, I'm going to have to do partial fraction expansion. The first thing you should do is solve for the roots. And then once you have the roots set up, okay, is it complex? Does it already look like the table? Do I need to do any manipulation? You may not need to, but that's a common mistake too. People immediately try to go and make it look like the table, and then they end up with e to the negative j whatever in their final answer. That does not exist in the time domain. If you can go build me a function generator that can make e to the j omega t, you'll be worth billions of dollars. That doesn't exist. But I can make one that does sine and cosine, right? I can have sine waves and cosine waves. You can do a function generator that can do that easy. So make sure your answers in the time domain don't have e to the negative j 2t or something like that in there, because that's not something that you could go ahead and replicate. And what we saw in one of our last classes, was it our last class? That was the one before that. In our, no, it was the last class. Remember how we came up with a solution to a circuit and we modeled it in multisim and came up with a plot? We did the same thing in Excel that we got from doing partial fraction expansion and got the exact same curve. So we can check our results. So it should be something that you can plug in values of time and you can get some realistic answers there. Otherwise, you know, why would we do all this stuff? And that's all the brain dump stuff that I could do. I didn't include any exam one stuff, but at this point, almost all that exam one stuff should be burned in your brains, right? KCL, KVL, loop equations, nodal analysis, Thevenin equivalence, Norton equivalence, max power transfer, all that stuff. That stuff is like, hopefully, maybe not max power transfer or superposition, but all the other stuff that we talked about should be something that if you're going to be analyzing any circuits, it's really helpful for you to be pretty darn good at doing that stuff, or at least understanding the concepts of it. Because all of the classes that you're doing here are all based on like those 3 or 4 theorems, right? Every single class that you've done is based on, hey, the current's got to go someplace, and here's where it goes. So it's KCL. It really, when you break it down to that, it makes electrical engineering much, much easier because like, wow, that's simple. And it actually is so simple because in all of electrical engineering, you can have 4 equations that can model any system in electrical engineering. They're called Maxwell's equations. Any of those 4 equations will get you your end result. All right, I'll stop yapping. Questions? Yes, ma'am.
Is this exam review going to be on Brightspace?
I can put it there if you think it's useful.
Yeah. Also, give us the operation table into.
Yeah, I can put the operations and the Laplace table and this. I'll combine them all in one document and do that. Sure. That's easy peasy. Feeling more comfortable now after going through this, all this stuff jarring memory, or you're like, oh, well, maybe not. It's only been about 3 weeks of new material, right? It really is only 2 chapters, isn't it? The first exam, I think, was what? 4 chapters worth or 4 modules worth. This is basically first order circuits and Laplace. But the most important thing you'll get out of this class for this semester is the Laplace stuff, in my opinion. That is by far the most important. And it's not anything more than, you know, as you graduate and you work out in industry, that they're going to expect you to be an expert in Laplace. It's just being able to have that strong fundamental understanding. Hey, I can do circuit analysis. I can always go back to Laplace. You never know what your career holds. So maybe you're going to be working in the utility industry and you're going to be looking at switching transients. Like you got a computer program that's telling you, hey, the voltage across the switch is going to go to 150% of nominal because of the switching transient. Is that right? You can do those programs do all the same thing with Laplace. You can do all that in the Laplace domain. There's an actual book. I have a copy of it if anyone looks at it. It's called Electric Transients and Power Systems, and it's all in Laplace, the whole book. But it's all, if you can do this stuff, it's all stuff that we've seen here. Any questions?
If I give you like, could you do another homework problem?
Sure. Which one? 2D? On which homework? Do you know what it is? You want to just tell me, or do you need me to look it up? Okay, just give this a second to boot up. All right. Oh, somebody has a chat. Yes, you get both sides of the note card.
F equals 9 over x squared plus 6s plus 25.
All right. First thing I'm going to do, quadratic equation, right? Always figure out the roots. It just makes it so much easier. Negative b plus or minus b squared minus 4ac all over 2a. Negative 6 plus or minus the square root of 64 negative, which is 8j over 2, which is negative 3 plus or minus 4j, right? When we have complex roots, it behooves us to write it in this form, right? S minus the real part plus the imaginary part squared. Correct? Do I have 2 functions that are multiplying each other here? The answer is no. I only have 1 function, right? So I'm going to break this up into 2 parts. And now in the Laplace table, I know that if I have s over s plus 3 squared plus 4 squared, move my 9 out front, this looks like the cosine waveform, right? Or the cosine function in the Laplace table. And over here, this kind of looks like the sine function, except for the sine function, I need omega here. Omega is equal to 4. So out front, I move the 9/4, right? I move the 9 out and then I divide by 4. So in the Laplace domain to the time domain, this becomes 9 e to the minus 3t cosine of 4t plus 9 over 4 e to the minus 3t sine 4t. Did I do partial fraction expansion? Nope. I didn't solve for any coefficients. I just made them look like the Laplace table. So that's my suggestion. Make it look like the Laplace table. And the first thing I had to do was figure out the roots of the problem. What are the roots? Quadratic equation. Easy peasy. Does that answer your question, Homa? I mean, does that make it clearer or less clear?
I just got. When. Like it made sense when we both decided, but then I was before.
Yep. So the reason why I knew it would work, I have to have omega over here. So instead of trying to get fancy, I just move this coefficient out front and multiply it. And then because I multiplied it by 4, I had darn well better divide by 4 to make sure I'm multiplying by 1, right? So if I multiply by 4 over 4, isn't that the same thing as multiplying by 1? Which algebraically I can do all day. I don't change anything. Multiplication by 1 just means it's the same thing. So that's why I did 4 over 4. Other questions? Going once. Twice. 3 times. What's that? 3 times a lady. So what we'll do is on Thursday, if you have a couple questions, we'll spend a little bit of time just for a couple questions. So make sure you have valid questions before we just have to keep covering new material, right? And so like today, I don't want to cover new material because I give you this time as, okay, you got to study for a test. I give you that extra time. I don't want to try to put new material in there because it's going to confuse you. But we do have to start covering new material. And so you can come to class with any questions and go from there. Because class time is very precious. But the test time, I try to give you a little bit of a break. You get one review session and then post, we just get to go over the tests. That way you can kind of like, okay, I don't have to put my thinking cap on that day. That's all I had. Y'all can go. Had a lot of time, but this is your review session. So if you don't have questions, then it's your time. So it's fine. Imagine if I didn't put together that little half-page stuff. It'd have been here for 3 minutes, right? So kudos to me. So, all right. Well, if there's nothing else, have a great day, y'all. See you all on Thursday. Take care.
Thanks, Paul.
Thank you.